Now we introduce the notions of countable and uncountable sets. First of all, let's consider a simple example. Suppose we have this set A, B, C, D, and alpha, beta, gamma, delta, or 1, 2, 3, 4. So these are three different sets, but all of them have the same number of elements, four elements. So in this sense, we can always make a bijection between any of these two sets. And all of them may be abstractly represented as something like this: x1, x2, x3, x4. One of these corresponds to one of these. Not in any specific order, but in any order, but still we can make a bijection. More generally, if we have a finite set, x, then if its cardinality is n, then we can represent this x as something like this: x1, x2, and so on up to xn. So again, there is a bijection between the set of natural numbers from 1 to n to x. Okay, what if x is infinite? So that means it has infinitely many number of elements. Okay, and since you are familiar with this symbol infinity, but infinity is not a number actually. It is just a symbol that represents unbounded number. Okay, actually there are a few kinds of infinities, and now we talk about. Uh, Here's the definition. Uh, we say an, a set which is not empty is countable if its element can be enumerated, like enumerated, like x1, x2, x3, and so on. In other words, x can be represented as something like this. So sometimes this can be a finite set, sometimes it can be infinite set. But either case, uh, if as long as it is enumerated like this, x1, x2, and so on, then it is said to be a countable set. And a set is uncountable if it's not countable. Countable. It's just an negation of countable. And some mathematicians prefer to distinguish between finite and infinitely countable sets. But in our case, we just call both finite and countably infinite set as countable. Okay. So another way to put it is if there is a bijection between a subset of natural numbers and that set of interest, then that set is countable. Okay, the subset of natural numbers can be the set of natural numbers itself, of course. And here is a rather trivial theorem. A subset of a countable set is countable. Okay, so the set of natural numbers is countable. What about the set of integers? Is it countable? Actually, it's countable. What about the set of rational numbers? Rational numbers, are they countable? Actually, they are countable. You should try to prove that. Maybe we'll show that later. And what about the set of real numbers? Is it countable? It's uncountable. So, although the set of rational numbers and real numbers are quite similar, but there is a huge difference between them. Another example, which is actually which can be used to prove that this is countable, is this. Suppose X is the set of elements indexed by two natural numbers, where P and Q are natural numbers. So these elements can be arranged in a two-dimensional array, like a matrix. So x11, x12, x13, and so on. So this can continue forever. And x21, x22, x23, and so on. And x31, and so on. So is this set countable? Actually, it is countable because this two-dimensional array can be serialized in one-dimensional form. For example, first we write x11, so this element, and then we write x12, that's this element, and then x21, this element. So we go from here, then x13, x22, x31. So by make going like in this way, we can write down all the elements of this set in a line like this. Then if we just reindex these elements like y1, y2, y3, and so on, we can see that this set of two-dimensional array is actually countable. So by using this technique, we can show that the set of rational numbers is also countable, because 1, 1 may correspond to 1 over 1, and 1, 2 may correspond to 1 over 2, 1, 3 corresponds to 1 over 3, 2, 1 corresponds to 2 over 1, and so on. 2 over 2, and so on. So by this correspondence, we can show that the set of rational numbers is countable. However, this technique cannot be used for the set of real numbers. Now here's a theorem. That says the union of a countable number of countable sets is countable. Okay, so this may be confusing. The union of a countable number of countable sets is countable. Or in other words, the union of countably many countable sets is countable. So that means if we have sets x1, x2, x3, and so on. So this is no this each of these is a set, okay, and each of these is a countable set. Okay. This is countable, 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 and there are countably many such sets. Okay, then if we take the union x1 cup, x2 cup, x3 cup, and so on, this is countable. Okay, this is what this theorem says. So how can we prove this? Actually, we prove by using the same argument as this one, this example. So the elements of the set x1 can be written as x11, x12, x13, and so on. And the elements of x2 may be x21, represented as this. So if we take the union of all these elements, then its elements can be arranged in the similar manner as this one, this example. So we have x11, x12, x13, and so on, and x21, x22, x23, and so on. So this is exactly like the example we have seen here. Therefore, this union is countable. By applying this theorem, we can easily see that the set of integers is countable. So this can be expressed as a union of natural numbers, and negative integers, which is just negative of all natural numbers, and the set of one element, that is 0. So this is countable, this is countable, this is countable, or finite. Therefore, this is countable. The next theorem should be also almost trivial. That is the Cartesian product of a finite number of countable sets is countable. So that is something like this. If we have countable sets x1, x2, and so on up to xn. So this is finitely many sets, okay, each of which is countable. Then the Cartesian product, x1 times x2 times x3 times and so on up to xn is countable. So let's prove this. First, let's prove the Cartesian product of two sets is countable. So let A be set like this, and B be a set like this. Then A times B, the Cartesian product between A and B is A n B m, and m are natural numbers, right? So, but if we put let's say xpq as apbq, then the elements of A times B is something like this. PQ are natural numbers. And we have seen that this kind of set is countable, right? So therefore A times B is countable. And more generally, we can use mathematical induction. So x1 times x2 times and so on up to n can be expressed as this: x1 times x2 times up to xn minus 1 times xn. So this is a Cartesian product of n minus 1 sets. But this is a set anyway. And by the induction hypothesis, this Cartesian product is countable. And by assumption, this xn is countable. So this is a Cartesian product of two countable sets. Therefore, as we have seen before here, this is the whole Cartesian product is countable. Okay, so that's the proof. But here, be careful. We have said that this is a finite number of countable sets. So what if this is, instead of finite, countably infinite number of countable sets? In that case, is the Cartesian product countable? So what I mean is this. So instead of stopping at the finitely many sets, what about this? So this product continues forever. I mean, infinitely many sets. The product of infinitely many countable sets. So is this countable? Actually, it turns out this is uncountable. You should try to see why this is so. As a concrete example of an uncountable set, consider the following lemma. Let A be the set of all mappings from natural numbers to 0, 1. Okay, so A could be written as something like this. So f such that f is a function from n to 0, 1. So the set of all mappings from natural numbers to this set of two elements. Then A is uncountable. We prove this by contradiction. Okay. So since we want to prove that A is uncountable, and we want to prove this by contradiction, suppose A is countable. Countable. So this means thus A can be represented as this. It can be any all the elements of A can be enumerated like F1, F2, F3 and so on. Okay? So each of these is a mapping from natural numbers to 0, 1. Okay? So if you feed any natural number to any of these functions, it will return either 0 or 1. So therefore, for every for every integer 1, 2, 3, 4, 5 and so on, there is a mapping that corresponds to one of these. Okay, so let's say if R is a natural number, there exists FR in A, right? So there is a mapping in this. Now, let's define a new mapping based on this set. Mapping G from n to 0, 1 by this. G of n is equal to 0 if f n n is 1 and 1 if f n n is 0. Okay, so if we specify this natural number n, there is always a mapping in this set A called Fn, right? And since this Fn is a mapping from natural numbers to 0, 1, so we can feed this n itself. So this n and this n are the same n, okay? If this function or mapping f happens to return 1 for this value of n, then we define g of n to be 0. And if this function fn happens to return 0 for the input n, then we define this function g of n to be 1. Okay? Since g is a mapping from natural numbers to 0, 1, of course, g should belong to this set A, right? So this means there exists some natural number r, let's say, such that fr is equal to g. So g is one of the elements of this set A. Okay. Okay, so if this is the case, then what is the value of g of r? What is it? If g is fr, then g of r should be equal to fr of r, right? But what's the value of this? This is either 0 or 1, but by the definition of g, so when r is when fr fr of r is 0, so if this is the case, then the value of g of r is 1. So this is a contradiction. Suppose, okay, maybe I should write like that. If this is the case, then by this definition, g of r should be 1. But g of r should be equal to fr of r. So this means 0 should be equal to 1, but this cannot happen. And if fr of r is 1, then g of r should be 0 by the definition of g. But this cannot happen. Therefore, either way, this is a contradiction. So g cannot be in. Therefore, g does not belong to A. I mean, this is impossible. So therefore, our assumption was wrong. That is, A is countable. This assumption was wrong. So therefore, A is uncountable. By using this lemma, we can prove that prove the following theorem. That is, the set of real number is uncountable. Okay. The proof of this is actually quite famous, so you should look for the internet. Maybe you should look for something called diagonal argument. Which is basically what we have done for proving this lemma. So we define something like this for real numbers. So suppose real numbers are countable, then it can be enumerated. Actually, we don't have to prove this for entire real numbers. All we need to prove is just between 0 and 1. Real numbers between 0 and 1. If it's uncountable, then R itself is also uncountable, of course. So all we need is this. And suppose this is countable, then it can be enumerated. Then we can define something like this, this function g. And then it will lead to a contradiction. And this kind of argument is called diagonal argument. You should try to look for it and try to prove this theorem.